Okay, I guess we should probably get started here. Thank you all for joining me. I know it's me between you and beer, so we'll try to make this quick. If you have any questions, try to hold them to the end. If you can, feel free to raise your hand and interrupt me. My name is Krug. I am the principal now solutions architect here at Couchbase. I also manage the West Coast and Central regions pre-sales teams. I've been with Couchbase for about 5 years. And today we're going to talk about sizing. And sizing is really the concept of how many nodes do you need for a given Couchbase deployment, and then talk about some of the deployment considerations that relate to and affect sizing. Just turn this 1 second. So first of all, a shameless plug for a blog series that I wrote a little while ago. It's a 4-part, hey Jay, a 4-part series going through a variety of sizing topics. A lot of what I cover here is kind of the thin veneer into that, and then this blog is a pretty deep discussion of all of the different factors, going through some more monitoring and specific hardware deployment characteristics. You can find this on blogs at blog.couchbase.com. I tell people to search for how many nodes Couchbase, and usually this one pops up pretty quickly. So sizing a Couchbase cluster. Sizing is really the biggest factor in terms of the performance that you're going to get. It used to be the biggest factor in terms of stability as well, but we've fixed a lot of those bugs. So now it's really just about performance. You want to focus on serving as many reads as possible out of RAM. And you want to make sure that you have enough I/O, enough disk I/O, enough network I/O for the writes, many other operations that are going on that are going to contend for and consume that I/O. And then another really important part that sometimes gets lost is having enough nodes and sizing properly to mitigate the inevitable failures that a system is going to have, be it hardware, software, network. And with Couchbase, everything we do really scales out. So the more load that you have to sustain, the more aggregate RAM you need, the more aggregate I/O that you need, you can get that by scaling out or by scaling those systems up, by allowing each one of the systems in a cluster, each one of the nodes in a cluster to handle more and more, allows you to scale up, but you're also going to be benefited and get a much more aggregate capacity by scaling that out. So one of the recurring themes that I talk about a lot, that this blog is really written around. Can you guys see? Am I blocking any of the slides for you? Okay. Is these 5 factors that really determine how many nodes you need: RAM, disk, CPU, network, and that concept of data distribution, data safety. And we're going to talk about all of these in more depth. But really, it's going to be one of these 5 factors that determines how many nodes you need. As we'll see, certain workloads are benefited by having more RAM. And so the more RAM you need divided by the amount of RAM on the nodes you have, that's going to say you need 10 or 15 nodes, right, by your calculations. It would be very rare, or scratch that. You may need 10 or 15 nodes. And then, on another hand, you may have a workload that's fairly write intensive. In order to get the enough aggregate disk I/O, you need 10 or 15 or 20 nodes spread across the I/O layer that you have. And so it's going to be one of these factors that's going to dictate how many nodes you need, where the other factors are going to come along with it. So for example, in those cases, if you need 10 nodes worth of the RAM to store the data set that you want to cache, you're going to have enough disk I/O to sustain the writes that are going into that system. If you have more writes but a smaller amount of RAM or amount of data, you may have a smaller RAM requirement but still need 10 or however many nodes in order to distribute those writes. So it's important to understand your workload in the context of which sizing factor is it bottlenecked on, and then make sure you size your cluster so that you have enough of that one where all the others come along with it. And as we'll see, RAM and disk are really the 2 most common bottlenecks, the common sizing factors. It's usually either an amount of RAM or an amount of disk I/O that dictates how much you have. CPU and network, while they can be considerations, generally aren't. There's generally enough CPU cores within a system. There's usually enough network that it's not a problem, but you can't forget it. You have to keep in mind that you are using CPU resources, you are using network resources, and so if you have one of those few use cases that fits on the outer edges of things, that might actually be the bigger factor. So let's talk about each one of these in a little bit more depth. RAM sizing, the most important part of this is to keep your working set in RAM. And the overall RAM that you're going to need is made up of the managed document cache that's based upon memcached within each node of Couchbase. And that is the metadata, that is the working set, some associated metadata, and you want to keep in mind that both the active and the replicas should have sufficient RAM so that if you have a failure, you're not reading all of the replica data from disk. There's a little bit of nuance here across different versions. So before 3.0, all of your metadata for every document in the system needed to remain in RAM. And so even if your working set was relatively small, as we'll talk about in a minute, you still had potentially a large amount of RAM being taken up by the metadata for tracking all of the documents in a node. And that has a really strong advantage in terms of doing lookups, especially for data that doesn't exist. For a node to be able to turn around to an application on a request and say, I don't have that data, it can do that very quickly when it knows all of the data is in RAM. That has the trade-off of having to use more RAM. So in 3.0, we added a mode that you can switch on a per bucket basis between keeping all of the metadata in RAM at all times or allowing some of that to be removed from RAM as you fill up the RAM along with the other data that's being ejected. And so that has the benefit of not using as much RAM for a very, very large data set, but the performance trade-off of not having quite as fast responses for data that's not in RAM, especially data that doesn't exist. And so you can choose that on a per bucket basis. So even within one cluster, you could have 2 or more buckets in different modes. But it's important to understand the trade-offs that you're going to make when choosing one or the other. And it's really obvious right in the bucket creation screen. The other part of RAM in general, and this is headroom that you want to leave outside of your cache quota, is general file system buffer, depending on how much view activity you're going to have. This is only relevant up to this is only relevant for views which don't have an actively managed caching layer. If you've attended any of the sessions about our upcoming 4.0 product, that adds a layer of or adds a component of secondary indexes that do have a managed caching layer within them, and that's a different part to talk about. I'll cover some of that at the end of the presentation. But if you're heavy users of views, leaving more headroom and more RAM available on the nodes will give you better performance from them in general. So let's just take a couple more minutes and go into this in more depth. Focusing on the working set for a minute, these here are 3 examples of what we would describe 3 different types of working set. There on the left is a very small amount of data that's being actively accessed, either read or written, when compared to the overall data set. So this is very common of, let's say, a user profile store, where you might have hundreds of millions of users in your system, but only 10% or 1% of them are really active on the system at any given point in time. You can size your working set for a much smaller amount than the overall data set has. In the middle is somewhere a little bit closer, where you have, let's say in this example, only 1/3 of your overall data set you want cached in RAM at any given time. And so you would tend to allocate more RAM in relation to the overall data set. And then on this far right-hand side, an application where part of the use case is to keep all of the data in RAM. very common for heavy caching use cases or ad targeting use cases where you have a very, very random access to all of the data. You don't have the concept of a working set, which means all of your data needs to sit in RAM all at the same time, even as it's persisted to disk. And so the understanding where you kind of fall, where your workload and application falls, will dictate what ratio of RAM to data set size is optimal for your application. And this is set at a bucket level again, so you can have 2 or more buckets sitting side by side with different RAM configurations for different sizes of the data set underneath. And then I mentioned earlier, when we talk about the view and index I/O buffering and caching, we've done a few benchmarks showing that the more RAM you give to a node outside of that buffer, outside of that caching layer we were talking about earlier, the better the view responses will be because they can be buffered and sent more from memory than from disk. As I mentioned, and I'll talk later, the secondary indexes of 4.0 actually do have a settable and managed caching layer. The second factor, again, depending on workload, can be the more important or the more deterministic one, is disk. And disk is usually broken into I/O, read and write, throughput or latency, and overall space. Usually space is not a big problem for most deployments. You have disk is fairly cheap to get in large quantities. But if you're in an Amazon deployment or a cloud deployment where you are restricted or actually have to pick how much how much disk size you give to a given node, then it becomes something that you have to think about. And so we include it here. The I/O is usually constrained by the amount of write load your application is putting on the system. Let me just see what my next slide was. And I have a very important word up there is the word sustained. And sustained means over time, the overall amount of write traffic that you do needs to be able to get to disk eventually. But because of our, I'll just go into this now, because of our caching layer, Couchbase can sustain bursts of writes that are not matched by the underlying disk. And a burst could be for 1 second. A burst could be over the entire peak time of your application, over a series of hours. And we have customers that certainly run over time. Their disk write queue goes up and up and up into the many thousands or even hundreds of thousands. But then at the end of the day, at the end of their peak cycle, it comes back down and is able to be drained down to disk. Sometimes this is a daily cycle or a weekly cycle. And the point being that the application has not seen any difference in performance. It's able to continue writing into the system without being slowed down because the disk is not quite able to keep up with it. However, over time, and whatever your time period is, whatever your cycle is, you want to make sure that that eventually does drain down to near or at zero, so you can ensure that you do have enough overall capacity. And if you see that queue getting higher and higher each day, or reaching a higher low point each day, that's an indication that you don't have enough disk I/O throughout the whole system. The disk throughput is certainly affected by the speed of the disk. SSDs are faster than spinning disk. Spinning disk is usually faster than say Amazon EBS. We have some customers here in this room actually who are using Fusion I/O underneath their Couchbase nodes. They're getting extremely high throughput in the order of 150,000 writes per second to disk on an individual node. But they're paying for that by those Fusion I/O cards, and they have a very high, over 1 million write per second workload of fairly sustained writes that they need to get down to disk. Other customers have more read-heavy or just generally less write-intensive applications and can get away with either spinning disks or cloud-based disk systems. Generally, RAID is there for more throughput, not so much for more redundancy. Couchbase, as you know, has the redundancy built into it at an application layer. So adding a RAID level for redundancy, RAID 1 for instance, adds more of an impact on the performance. So you don't need to take that hit, whereas RAID 0 striping or RAID 10 with better throughput overall can be useful, but really isn't incredibly necessary. The interesting thing about disk throughput is that it's a relatively finite resource, and there are a variety of workloads that contend and take up that resource. So your read and write workload, especially your write workload, but if you're reading more data from disk, that needs to have enough throughput. But there's also things like compaction going on at the disk layer. You may be taking backups off of disk, rebalancing, maybe reading data from disk in order to send over to another node. So all of these things are going to contend with the disk, contend for the disk I/O, and may limit the overall amount that you have for actually writing data to disk. All of these different factors are hard to measure. It's hard to know the effect of each individual one as it comes into the system and goes away. So what we use and what we recommend our customers look at is that disk write queue. The disk write queue in the UI or in the other in the monitoring metrics is the number of items that are waiting to be written to disk. And that's a great proxy metric for knowing whether you have enough I/O overall. So on one hand, you could be writing in very quickly and just purely not have enough disk I/O to get that data down to disk. Or you could have a reasonable write workload that you say, oh, I should have enough disk I/O to handle this. But when compaction kicks in, that queue starts to grow because now I don't quite have enough to get it down. Compaction finishes, the queue drains, and everything's fine. But if it doesn't, or if compaction is continuously running and causing that queue to grow higher, that means that overall you don't have enough disk I/O. So disk I/O is a harder factor to measure very mathematically. It's more of an observation of seeing if, with everything running together, do I have enough disk I/O? What else? The 2.1 comment is somewhat old. In anything after 2.1 and later on, we have multi-threaded disk readers and writers. In previous versions, we had one thread for reading and one thread for writing, and that limited the overall throughput that we can get. Now we have, in 3.0, we have a dynamically tunable number of reader threads and writer threads. Now, when we come back to disk space, there are some parts of this to take into account. Obviously, your overall data set is going to sit on disk. Your data set and any replicas are going to sit on disk, so don't just size for one copy of the data. And the other factor is that our storage structure is an append-only file format. That means that every write to disk is a new set of data on disk. Even a mutation to an existing piece of data is a new entry on disk. And that means that the file will continue to grow theoretically infinitely, right? But what we do to prevent that is we have compaction. And compaction comes along and it finds only the active copies of the data. It rewrites them out into a new file and it deletes the old one, therefore saving you space. But depending on your workload, you may need more or less disk space so that those files can grow and shrink over time. And in order for compaction to happen, it does need to create a temporary copy of some of the data. And so that growth and shrinkage of the files, as well as the intermediate rewriting of them, means you may need more disk than you would otherwise think you would need. This is mostly a factor on very update-heavy workloads. Read-only doesn't affect the disk. Insert-only is really only inserting new copies of data, so it makes sense that you would have a growing disk file. But if you have a lot of updates going on or a lot of deletes going on, which are basically updates, you're going to have more variance in your disk size. And so making sure that you have enough headroom for the files to grow and shrink within, that you don't reach an out-of-disk situation is part of understanding that use case and being able to monitor and understand what you're seeing when you see the disk files grow and shrink and when you see compaction running. Okay. CPU, as I mentioned, is usually not a big factor in sizing Couchbase. On one extreme, if you're doing just primarily key value workloads, you'll see almost no CPU usage or very, very low CPU usage until you get into the very extreme of throughputs. The more writing you do, the more the data that has to be written to disk, the more CPU is going to be used in writing to disk. The more you leverage views, the more you leverage XDCR, the more buckets you have, the more CPU cores you're going to want. Couchbase is a very, very multi-threaded, multi-processor ready kind of system. And so as you do more with it, adding more cores will allow all of those operations and internal functions to happen in parallel. Certainly, and in some technologies, there's this idea of starting up multiple instances of a given technology or a database on a single system in order to make full use of the resources there. That's really not going to be a problem with Couchbase. You're better off allowing one instance, one copy of the software to run on a given host, on a given operating system, and let it use all of the resources that it can. Especially with the latest software, the ability of multi-threaded I/O processors, multi-threaded data and application connection handling. We can easily saturate disk I/O, except for Fusion I/O at the very edge. We can easily saturate a network. We can easily saturate the CPU. So there's no need to think about having multiple instances just because you have a particularly powerful box. This is just some general minimum requirements, 4 cores or 8 cores, depending again on what your level of usage is of the system. The more read heavy you are, the less CPU intensive it's going to be. The more write heavy, the more CPU. The more sensitive you are to getting data up to or down from disk, or down to or up from disk, the more that you'll be benefited by having more CPUs and allowing that to happen in parallel. With views, with XDCR, generally want to have more CPU cores so that all of those things can happen in parallel. Network is usually almost not even worth talking about, but keeping in mind that there is network traffic being used, writes into the system are going to be multiplied by how many replicas you have, so that's going to increase the overall bandwidth. Doing rebalancing is going to pull data off of one node and send it to another. That's going to use some network traffic. XDCR, especially between clusters, you want to make sure that your WAN between those is sufficient for your requirements. You know, if you have a very constrained WAN, be aware that the data is not going to get to the other side as quickly as you might otherwise want it to. The more bandwidth you can give there, the faster that will work. It is probably possible that Couchbase can saturate a WAN network, so make sure that you have that sort of network configured properly, or you turn down the replicators on the Couchbase side so that it's not replicating as fast and saturating that network that would otherwise hurt other things that are on the network. The other thing that's very noticeable with Couchbase is the latency of the network. And so with single gig networks, we tend to get 500 to 600 microseconds for response times. With 10 gig E, we tend to get around 200 to 150 microseconds. I was doing a benchmark in Amazon the other day with a VPC of 10 gigabit and enhanced networking, and I was consistently sub 100 microseconds, which is very, very, very fast. And Couchbase will make use of that latency. Because of our caching layer, we can put data on the network and we can respond to requests from an application in tens of microseconds, that any added time in terms of response time is the network. So when you make a request to Couchbase and you get a response back in 1 millisecond, that 1 millisecond might be good enough for your application, but 90% of that is taken up on the network. And so the lower latency, the higher throughput your network is, the faster you will get back. Again, you have to understand what your requirements are. Some applications, 1, 2, even 3 milliseconds is perfectly acceptable. Other applications need to have the lowest latency possible, and you will be benefited and you will notice the difference moving to 10 gig. Latency is also affected somewhat by object size. Obviously, a 500K object takes longer to transfer over the network than a 500 byte object. And so, again, if you are particularly latency sensitive, the smaller objects that you're working with, the faster you'll be able to get them back. The last factor or thing that we're going to cover before moving into some other stuff is this idea of data distribution and data safety. Servers are going to fail, right? You need to be prepared for that. And one school of thought might say, I have one node. If I create a second one and replicate it, that should be good enough, right? We actually recommend at least having 3 nodes for any sort of production environment. The reason being a couple fold. Obviously, one node is a single point of failure, and everybody knows that. 2 nodes provides replication, but if one of those nodes fail, now you have a single point of failure again, and we want to avoid that. With 3 nodes, you can allow one to fail and still have some data replicated, still have 2 nodes still supporting the system. With 3 nodes, you have the ability to remove one of them, do any upgrade or patching on it, while the other 2 are still replicated and not putting your data at risk. And with 3 nodes, we can be sure that a failure of one of them is not creating a split brain. So Couchbase's automatic failover is only enabled when you have 3 or more nodes, so that if one of them fails, the other 2 know that there's only one down. If you imagine a situation of 2 nodes and there's a network link that goes missing between the 2, they both think the other node is down, they both fail each other over, and now you have the same data active in 2 places at once, which leads to inconsistency of the data and might cause corruption up in your application. So we explicitly don't allow that at 2 nodes, but it's enabled at 3 so that we can be sure we only have one node split off from the network or failed instead of multiple. Okay, so just to recap, and then I'll take questions for a couple minutes. The 5 factors that we talk about in sizing, RAM and disk being almost always the most important. For more heavy caching workloads, RAM is usually more important. For heavier write workloads, disk is going to be. And then depending on your own environment and the constraints of CPU, the constraints of network, you may need to take into account other parts of this and always have at least 3 nodes. Before I move into kind of a departure from this, are there any questions that you've been burning and dying to ask me? Yes?
For a backup that's running, what's the impact on RAM?
So good. The question was for a backup that's running, what is the impact on RAM? As small as possible, and we do as much as we can to prevent it from being so. A backup, when it runs, you have the ability to choose either just the data that's on disk or pull the most consistent copy from RAM as well. So you get a level of decision there. If most of the data is in RAM anyway, when you're pulling a backup, it will stream the data from RAM and then pull up and copy over one-off requests for any data that's not in RAM. If most of your data is not in RAM, it will start backfilling that from disk and sending over to the backup. Now, that backfill we do in chunks so that we don't overwhelm the RAM that's already there. So the goal is not to pollute the cache. The goal is not to create a large amount of ejections. At the very edges of memory usage and depending on your incoming write load, there may be more of an effect, but the design of the system is such that it doesn't. Yes? You know we haven't released the software yet. The question was, yeah, I know. Well, we keep selling it. We just don't have it yet. The question was around the index and query servers. I have a couple slides on it at the end, so I'll let you save your question for that when I get to it. Less guidance than you would like, more along the way. Yes?
So if you have a write-heavy document in time delay, what's the limit of ransom you have to worry about? This requirement, you don't have to worry about that.
So let me see if I got the question right. You were asking a write-heavy use case with short or relatively short expiration TTL on it. What was the rest of that question?
So do you have to worry about this requirement of the write-heavy requirement, or is it mostly RAM?
I see. Is the requirement more around the disk or the RAM? It depends on how heavy the writes are and how much of the data set is changing at any given time. For that sort of use case where the data is very temporal and you don't necessarily need it persisted to disk or you don't worry about it getting persisted to disk. Oh, only 10 minutes, huh? That'll be interesting. You generally want more RAM so that you keep that data in RAM. It'll expire and be cleaned up. If it hasn't all been persisted to disk, it won't really matter. It'll get there eventually. So you can run that sort of workload with a higher disk write queue than you would otherwise have for something where you actually have that data persistent and need to keep around. Does that make sense? OK, let me hold off on questions and get through some of these slides, and then we'll have time, hopefully, at the end. So just running through a couple kind of best practices and deployment considerations. I covered most of this in a previous slide. We really recommend, as much as possible, using local disk. The question always comes up, can I put Couchbase on top of a SAN? And yes, technically it will work, but really that starts to break your scale out capability. So you have all these great scale out, shared nothing at the Couchbase tier, all coming back down and sharing a single point of failure, a single point of bottleneck in the SAN. We do have customers that run on top of SANs. We do support them. They do tend to have problems with the disk system being able to keep up, especially when rebalancing or dealing with very heavy write loads because the data is getting replicated and then written down to disk in multiple copies. So as much as possible, staying away from a centralized file storage. But if your system requires it or your environment really requires it, then making sure that it has enough I/O and latency to meet your needs. Talked about a lot of this. Let me go through a good conversation about virtualization, cloud. We have a solid 30 or 40% of our customers deployed in EC2. We have a large number of customers deployed within their own VMs or private clouds, and we have a large number of customers deployed on physical hardware. There certainly are differences in the performance between them. It's really up to your environment to understand that trade-off between the automation and administrative benefit of a virtualized or cloud infrastructure versus the performance overhead that you're going to incur. We do see generally more nodes overall in those virtualized and cloud infrastructures than you would otherwise need in physical hardware. But again, it's all a trade-off that you have to be able to make for your own considerations. This is fairly redundant. Currently, the R3 and the C3 instances are generally the best for Couchbase up in Amazon. You get a good mix of CPU and RAM. They all come with SSDs, local SSDs. So those would be my first choice to look at. If you're being forced into something much higher, the i2s tend to come with more RAM and CPU overall for a very scale-up deployment. I'm going through this pretty quickly. Couchbase, we do have the ability to group nodes within a cluster across availability zones. This is called our rack zone awareness. It was released in 2.5, and it allows to ensure that the replicas for the data set are only contained in another group of those nodes within the same cluster, so that an entire group, an entire rack, an entire zone could fail, and you still have the full copy of the data set. I'm going to skip through some of this, and these slides are available in various forms, and get into the 4.0 discussion that I hope more people are interested in before I run out of time. So the sizing of 4.0, the same 5 factors apply, right? They come about in slightly different ways depending on the different service, but they do still apply. As we talked in the various sessions and the keynote earlier, multidimensional scaling gives you now the ability to size and scale out different services independently. The data service is what we've been talking about this whole 45 minutes or so. That's still, well, let me just go to that. That data service still applies and still has all of the same discussions that I just went through in terms of RAM for caching data, in terms of disk I/O for throughput, in terms of the CPU for the views and cross-data center replication, and all of the kind of the minimum requirements for that still exist. On the index side, This is the new to 4.0 indexes, otherwise known as GSI, global secondary indexes, or just secondary indexes. These are going to be primarily RAM and disk I/O bound, and arguably more disk I/O bound than the nodes running the data service. With the data service, you can distribute all of the writes across all of the nodes, and by adding more nodes, you get more disk throughput. With the secondary indexes, you're going to be consuming all of those writes or some subset of those writes into one or a few smaller nodes or a smaller number of nodes. And so you'll want to scale those up in terms of disk I/O if you have a heavy write workload. You can put in more SSDs, you can put in faster SSDs, you can put in Fusion I/O. The benefit of this multidimensional scaling is that you can spend for Fusion I/O on 2 or 3 nodes holding the indexes and not have to spend it on all the other nodes handling your data service. So that's where that trade-off and benefit can be made. Whereas the data nodes have the nodes running the data service has the data replicated peer-to-peer all within them. With indexes, we really just have one index replicated multiple times for HA and a little bit of load balancing. And so in the first version, you have to set that up manually. Eventually, we will do that automatically for you. But generally, you have one node handling your primary index load and another one that has the index replicated to it. And if one fails, the other will take over that load. Also, the more RAM that you can give to this, the more of the index will stay in RAM. This is using the new ForestDB persistence engine that we developed. That's not yet part of the data service, but it will be into the future. But all of our index service is built on top of ForestDB, which comes with its own managed caching layer. And you can define an amount of RAM that you want it to use, and it manages that so that you can have some or all of the index cached in RAM and be able to rely upon that rather than just the file system buffer. So the more RAM that you give to that, the more you'll be able to utilize that. On the query service, the query engine, very, very low disk and RAM requirements, much more CPU heavy, much more multi-threaded in order to do lots of concurrent queries and handle lots of concurrent connections. So the more CPU that you can give to the query service, the better it will be. And again, if you contrast that with the data service, it has relatively low CPU requirements as long as you're not putting a lot of extra load on it. And the same thing applies with HA for the query service. It's completely shared nothing and stateless, so you can add as many as you want, but 2 gives you HA. So the minimum production cluster, I'll come back to this in a second. The minimum production cluster now becomes 3 nodes holding the data service, 2 nodes holding the query service, and 2 nodes holding the index service, so that you have everything properly replicated for high availability. That would be the best practice for a reliable production deployment. You can run all 3 services on as many nodes as you want. And so one single node with all 3 services turned on to an application still looks the same as 100 nodes with all of these services isolated amongst them. All of the client library, topology awareness, and intelligence still remains. So you don't have to worry about developing on your laptop with one node that has all 3 services and then turning that on to a cluster that may be configured very, very differently. Or maybe replicating that cluster to a different one that's configured differently. They all respond the same in terms of behavior to the application. And that's a really important part to make sure that we all agree upon. So I talked a little bit about this. Actually, this is kind of the same thing that I just mentioned. So this gives you a kind of a pictorial view of what the combination of workload isolation and scale up within scale out looks like, where the query service is isolated to 2 nodes that have lots of CPU. The index service is isolated to 2 nodes that probably have much higher disk I/O, disk throughput, and RAM capabilities. And the data service spread across 4 or any more numbers of nodes, because the different workloads, the different services, like to use resources in different ways. If we had all of these co-located on the same nodes, which is possible and completely functional, you have all of the different workloads contending with each other, and which basically means you have to size for the biggest one, or even for the aggregate of all of them. With this multidimensional scaling, now you can size the different services depending on the type of workload you're putting on it and the way that each of those services is best benefited by the resources available to it. So in just wrapping up, sizing is always going to be tricky business, right? It's always somewhat more of an art than a science. We have various calculations and internal knowledge to be able to take your requirements and spit out a recommendation, but it's always got to be wrapped in the awareness that a production environment is what is going to tell you what actually is behaving with your application. We've had lots of customers do synthetic workload injection and say, oh, it looks like I need 10 nodes to do this, turn their application on it, and the way their application was writing data or working with it was just completely incongruous to how that synthetic workload was, and we in fact needed to have more or tune things in a different way. So as much as you can do to test beforehand and match it up with your on-paper calculations, and then constantly monitor your production environment. Constantly monitor and revalidate your sizing to say, I thought that 10 nodes should be sufficient. Is my cluster behaving that way? Am I getting the right disk drain rates? Am I getting the right RAM utilization? Am I getting the right performance out of it? And having that constant feedback loop for what you're doing in production to what you think the cluster should be sized for. That's fine. And then there's a lot of good information up in our docs. Again, a shameless plug for my sizing blog. Probably sit down with a cup of coffee. It's a good couple-page long read, so it'll take you a little while. But I think there's a lot of really good information in there. I've had a lot of other people tell me that, so I'm not just touting my own horn. And yeah, and work with us. Let us help you. Let us give you the best current guidelines and recommendations that we have. You know, we're learning about our software as well as time goes on. We're learning about how all these different factors come together, how different use cases create different considerations. So the more we can give to you, the better your experience will be. I think I'm just about out of time, so I thank you very much. I'll hang out here for a little bit. I know I didn't get to answer a whole lot of questions, so if you have any, feel free to come up and ask me. Thank you guys very much.